All right, we technically have seen polar coordinates before. They are a different coordinate system that we didn't mention in the last video. We are going to kind of see them pop up again, and they are going to be very useful in our time in Calculus 3. So just a reminder about polar coordinates, what we can do is think of our standard XY plane, our Cartesian plane. So this would be X and this would be Y. And then if we have, say, a line or a point out here, which we might label as X naught, Y naught, we can think of extending a line segment from the origin to there. And with that line segment, we would say that there's an angle theta from the x-axis, and then this length here that we extend to is a length r. Okay, and then so consequently, we might remember this. Maybe we need a moment to review, but we end up with that if we want to find the angle theta here. Okay, certainly this is kind of x naught and y naught. So in this diagram that I have set up, we would say that tangent of theta is equal to y naught over x naught, or just drop the subscripts of zeros and you're fine. X over or y over x. Okay, and then similarly to find r, if we know that this is a right triangle, we can say x squared plus y squared is equal to r squared. Okay, and then just square root both sides, you're good. The other definitions that come with all this is that we can say x is r sine of theta, cosine rather. Cosine of theta, and then y is going to be r sine of theta. Okay, this all comes from right triangle trigonometry. All right. So that is everything that we have here. And certainly you could solve for tangent. Okay, so if we want to convert this equation r is equal to 2 sine theta into Cartesian coordinates, I would say why don't we try multiplying both sides by r. So when we do that, we get r squared is equal to 2r sine theta. And then r squared is x squared plus y squared is equal to, and then r sine theta, that was just y, so we get 2y. And then move the 2y over, and you'd have to complete the square and everything like that. And what you end up with is x squared, so I'm doing dot dot dot, x squared plus, and then y minus 1, quantity squared is equal to 1. Okay, and so you might recognize that as a circle with a center at 0, 1 and radius of 1. Okay, big deal. Okay, kind of stuff that we've already seen, but it's maybe been a hot minute since we've seen it. So now what we're going to do is extend polar coordinates into 3 dimensions. And when we do that, if you can imagine, polar coordinates are typically done in circles, and now you're just extending it up. So what do we get? We get cylindrical coordinates. Okay. So now we have our coordinates as r, theta, and z. Z just being your standard z variable from Cartesian. Some books do call it, instead of z, they call it an h. Okay, ours is just the notation we're gonna use is this first one. Okay. All right. So again, just to specify here, we'll draw a little diagram in 3 dimensions. Okay, so here's our 3-dimensional axis. Okay, we have x, y, and z, and so what we would think of doing is that, okay, first we're going to rotate from the x-axis by some angle of theta, and then we're going to go out a length of r. Okay, and I'm just going to do this in a dotted line, so that's r, and then we're going to go up in our z direction some distance, so then we go up, and that's going to be our point P. Okay, so this is some r, some theta, and some z. Okay, and we'll close that. Okay, and just a reminder, cylindrical coordinates, since they are an extension of polar, they have every same bit of piece of facts that polar does. So cylindrical, r can be negative, theta can be negative, z can be negative. That's all fine and well. Okay. So let's kind of think about these. I encourage you to pause the videos and kind of think through what the graphs of each of these would look like. Okay, and then when we resume, we'll go ahead and discuss. Okay, well, for this, in this case, when we say r is equal to a constant, and that constant is positive, well, you might just imagine, okay, so if we have a little graph here, we have some distance r, we go out, and then we're saying that no matter what our angle is, or no matter what our height is, it is just going to be along this ring. So then so that's kind of the perimeter of r, and then you extend it up and down, because we have, let me do different colors. And then we extend it up and down forever. So what do we end up with? A cylinder. Okay, and then now looking at the next one, well, if we're saying theta is equal to a constant, that means that we've rotated around an axis, and okay, so we've rotated, and then the distance that we go along that region, or along that angle of rotation, and the height is infinite. Okay, we don't really have a restriction, so we've rotated and it's anywhere along this line, and we just kind of extend it up and down, up and down, and so we get a plane. Let me redo that last line, or the whole thing. Something like that. So this one's going to be a plane. And more specifically, a full plane, okay? And we use full just because it's covering all, or I guess it's appearing in all 4 octants that it could, okay? And then this one, this is very similar to what we saw in Cartesian coordinates, but this would just be, if we are at a height c, it can extend in every direction, so this is going to be a plane at a height c. Okay. Alright, and so that's just kind of a brief overview of cylindrical coordinates. Again, the conversions, very similar to polar, it's just now we tack on a 3rd dimension.